Lightning is an electrical discharge in a charged cloud. For about a tenth of a second, the plasma channel it cuts through the air is hotter than the surface of the sun. Somewhere in the world, this happens 44 times a second. A typical cloud-to-ground flash produces a plasma channel more than 5 kilometers, 3 miles tall, running between a negatively charged cloud base and the ground below. The average negative bolt carries a peak current of around 30,000 amperes. Positive bolts, which are rarer but more energetic, can reach 400,000. A single return stroke lasts about 60 to 70 microseconds, roughly the interval between two consecutive frames of high-speed cinema. The channel reaches a core temperature above 27,000 degrees Celsius, close to 50,000 Fahrenheit, roughly 5 times the temperature of the sun's visible surface. Over the Earth as a whole, lightning occurs on average 44 times every second, or about 1.4 billion flashes a year. About a quarter of flashes are cloud-to-ground. The rest stay inside or between clouds, invisible from above unless they illuminate the cloud itself. The term of art for the ones that never leave the cloud is intracloud, icy lightning, and it is by far the most common kind. The charge has to get there first. Inside a thundercloud, small ice crystals carried upward by updrafts collide with larger particles of soft hail graupel, falling through the same volume of air. At temperatures below about -10 Celsius, each collision leaves the ice crystal positively charged and the graupel negatively charged. The crystals rise, the graupel falls. Over minutes, the cloud separates into a positively charged upper region and a negatively charged lower one. The electric field grows until the air, normally a good insulator, breaks down. The discharge moves in 2 stages. A stepped leader, too faint to see, advances from the cloud toward the ground in 50-meter steps, branching as it goes. When it is close enough to the ground, an upward positive streamer reaches up to meet it. The circuit closes. A return stroke then surges upward along the ionized path at roughly 1/3 the speed of light. What the eye sees as a single bright bolt is usually 3 or 4 successive return strokes, flickering along the same channel in about half a second. The electrical character of lightning was established in 1752. On the 10th of May that year, the French natural philosopher Thomas-François Dalibard erected an iron rod in the village of Marly-la-Ville, north of Paris, and drew sparks from it during a thunderstorm. In Philadelphia in June, according to the chemist Joseph Priestley, Benjamin Franklin flew a kite in a similar storm and observed the loose threads of the wet string repelling one another. Charge had passed down the line to a Leyden jar at the bottom, the first collected sample of a lightning current. Both experiments confirmed, for the first time, that lightning and electricity were the same phenomenon. 242 years later, the phenomenon acquired a second identity. In 1994, the Burst and Transient Source Experiment, a gamma-ray detector on NASA's Compton Gamma Ray Observatory, recorded short, intense bursts of gamma rays coming not from distant space, but from the upper atmosphere of Earth. These were named terrestrial gamma-ray flashes. Later observations by NASA's RHESSI satellite and by the Fermi Gamma-Ray Space Telescope's Gamma-Ray Burst Monitor showed that their photon energies could exceed 20 million electron volts, 1 million times more energetic than visible light. The current explanation, developed in detail by the physicist Joseph Dwyer, is that the extreme electric field inside a thundercloud accelerates seed electrons to nearly the speed of light. These relativistic electrons collide with air molecules and release gamma rays. A thunderstorm, in other words, is sometimes a brief particle accelerator. The distribution is not even. Most lightning happens over land, in the tropics, in the afternoon, where surface heating drives the strongest convection. The single most frequently struck place on Earth is the head of Lake Maracaibo in northwestern Venezuela, where a combination of warm lake water, surrounding mountains, and nightly winds produces storms on roughly 297 nights of the year. Satellite-based climatology from NASA's Global Hydrometeorology Resource Center records about 233 strikes per square kilometer there each year. the highest surface density of lightning yet measured. The ground-based worldwide lightning location network, with more than 70 very low-frequency stations around the world, tracks the same flashes by their radio signatures in real time. The plasma channel does more than make light. The temperatures it reaches briefly break the bonds of atmospheric nitrogen, a famously inert molecule, allowing nitrogen to combine with oxygen. The resulting nitrogen oxides fall with rainwater as dilute nitric acid, feeding soil chemistry. Before industrial ammonia fixation, lightning was a significant natural source of biologically available nitrogen. The reference textbook for the physics, Vladimir Rakov and Martin Uman's Lightning. Physics and Effects, published by Cambridge in 2003, runs to nearly 700 pages. The phenomenon is loud, common, and still not completely understood. The last decade alone added a new emission, the gamma-ray flash, to a process people had been watching for the whole of recorded history. Every bolt is the same event: a charged cloud, an insulator failing, a column of heated air collapsing into sound. It happens on this planet roughly 1.5 billion times a year. Most of them no one is watching.